So that was quite important. If you're a speaker tomorrow, or if you know a speaker tomorrow, 2 p.m. this afternoon is the deadline for seeing the person in the booth. So try to pass that word along. Otherwise, we're going to be have speakers left out in the cold, I'm afraid. Can I get that? There we go. Good. Okay, this is a panel discussion. And we have 3 panelists who I've invited to give brief talks each, something in the range of 10 minutes to get their ideas out there. And they are reflecting on the theme of this meeting, of this particular session, early life, minimal life, and I added synthetic life because there is a movement now toward understanding minimal life and early life by trying to put together systems of molecules that have the properties of the living state. Alonzo Ricardo this morning gave a wonderful introduction to this, so I don't have to say much more. I'm just going to show you 1 or 2 things that I think are important to what you're going to hear from the panelists, and then that'll remind you of any questions you have to ask the panelists after this session. One of the very first people to think about the possibility of early compartments on the Earth was Alec Bangham. And he gave a talk that in fact inspired my career in this area called Membranes Came First, with an exclamation point at the end of that, which is typical of Alec. Notice that in the old days, you had to draw your slide, you had to take a picture of it, and then you showed it with something called a slide projector. I know that most of you aren't familiar with that, but that's the way we had to do it. And he has an Earth there, he has a very thick ocean, and what you should notice is that as this chemical evolution occurs, there's an accumulation of what are called amphiphilic molecules at the air-water interface, and that these molecules can self-assemble into what are now called liposomes. Here's a picture of Alec taken about 10 years ago, and he's making self-assembled amphiphilic membranes in his backyard. All the people in this audience here, I'm sure, have done this, but I'll bet you didn't realize that you were making membranes similar to what we think were available on the early Earth as the first compartments for minimal life that gave rise to the life we have today. These membranes we now call soap bubbles, another technical term, and you're going to hear that word soap one more time because something very interesting has turned up in carbonaceous meteorites. We have discovered soap molecules in meteorites, and the meteorite organic amphiphilic molecules can give rise to the membranes that we think characterize the first life. This is an image that Alec saw under the microscope in the mid-1960s, and the main thing to realize is that as you look at these layers, these onion skin layers of this lipid vesicle, between the layers, those dark lines are in fact lipid head groups. Those are lipid bilayers, and the lipid head groups are juxtaposed one next to the other. One of our speakers is going to follow up on an idea that we've been working with, and that is an organizing matrix. That if you have molecules in solution as the liposome forms, they will be trapped between lipid bilayers in that multilamellar structure. They will be organized in a fluid matrix, and they can undergo polymerization reactions in that lipid matrix. When you then disperse that lipid back into a smaller liposomes, you have trapped some of those molecules. Now, when Alec discovered this, he called those multilamellar smectic phospholipid mesophases, which is quite a mouthful, so other people in Alec's honor call them bangosomes. Jerry Weissman called them liposomes, and you'll also hear the term lipid vesicles as we go on. Here's an image of the sort of thing that can be produced from extracts of organic compounds from a carbonaceous meteorite, in this case the Murchison meteorite. And years ago we found that they could self-assemble into very beautiful lipid-like vesicles that could encapsulate molecules such as these fluorescent dye molecules. Furthermore, we found that one of the major components of these membranes were fatty acids up to 9, 10, 11 carbons long that were components of the original meteorite matrix. We began to work on these, and Pierre-Alain Menard took this beautiful image some years ago, and this is decanoic acid stained with a fluorescent dye, showing how easy it is to make these membranes. Furthermore, it is even easy to capture large molecules, even as large as double-stranded DNA. These vesicles that you see are decanoic acid with DNA captured inside by a very simple procedure. They've been stained with the fluorescent dye so that you can see it. So we refer to these as protocells, and Jack Szostak's laboratory has taken up the protocell idea, and you saw this a little bit earlier in one of the other speakers, the idea that we can capture a partial double-stranded DNA inside a fatty acid vesicle, add activated monomers outside. They cross the membrane through transient defects, add themselves to the DNA, and then as the vesicle grows, it can even undergo a division. So these are steps on the way to what we think a minimal form of life would be. There's still a long way to go, but it's a good start. So I'm going to introduce the speakers now, the panelists. We have then Niles Lehmann is going to lead off. He's from Portland State University. Felix Olasagasti from the Basque Country in Spain is going to be our second speaker. Peter Unbrau, Simon Fraser University in Canada is our third speaker, third panelist. Their common theme is properties of nucleic acids such as RNA and DNA as related to this concept of minimal life. So Niles, would you come up, please?